In the last video, we reformulated Faraday's law of induction to be more explicit about the electric fields induced, and we revisited Ampere's law, adding a term to it that reflects that magnetic fields can also be made by time-varying electric fields. And this is called the Ampere Maxwell Law now. So those are two of the four Maxwell equations. And a third one of these you have already seen. That was Gauss's law for electric fields. That said, if I erect a Gaussian surface somewhere, the total electric flux going through it is equal to the charge enclosed over epsilon naught. Now, it turns out that there is indeed a Gauss's law for magnetic fields as well. And I would like to make this a pause the video challenge for you to come up with it for yourself. So go ahead, pause the video, see what you come up with, and then we'll compare notes. Alrighty, so keeping in mind that as far as we know, theoretical prognostications notwithstanding, there are no magnetic charges, no isolated magnetic poles. So whenever we see a magnetic field, it's got some sort of dipole action going on, like so. Yeah, something like this, let's say. So now if I erect any Gaussian surface, let's just make it this arbitrary potato shape here. However many magnetic field lines go in it, have to go out of it. So remember, inbound counted as negative, outbound counted as positive when we were doing this with electric fields. Same deal with magnetic fields. But here, however many go in, go out, because there's no place for magnetic field lines to either start or stop on. So this means that the total magnetic flux going through the surface, integral B dotted with dA, is just plain zero. And what this means is that there are no isolated magnetic charges. There is no north pole just sitting all by itself or a south pole sitting all by itself. Now, there are theoretical speculations about that. We know how to modify this equation if those theoretical speculations pan out. But to date, despite the better part of a century of searching, nothing has turned up, so I'm not exactly holding my breath. Anyway, with that, we now have the four Maxwell equations of electricity and magnetism. So it's probably good to write them down all in one place and discuss what they mean. So we will start with the two Gauss's laws. So we have the Gauss's law for electric fields. And that says integral E dot dA equals Q enclosed over epsilon naught. So what Gauss's law for electric fields is saying is that a way, not the only way, we'll see, but a way to make an electric field is to have electric charges hanging out. Electric field lines start and stop on electric charges. They start on positive ones, stop on negative ones. And that's what this is saying. Gauss's law for magnetic fields which we just came up with, says integral B dot dA is equal to 0. So again, what that means is that there are no isolated magnetic charges. Now we have Faraday's law of induction. We usually just say Faraday's law. So Faraday's law says that the integral of E dotted with ds, so this is for an integration path, is equal to minus d phi b dt. So this is saying that there is another way to make electric fields. If we have a time-varying magnetic field, we get electric fields, and the way this works, remember, is that these electric field lines will be circles that just loop back on themselves, or in any event, lines that loop back on themselves. And we will only have this electric field for as long as we have as long as the magnetic flux is changing. And then finally, we have the Ampere Maxwell Law. And this says integral b dot ds is equal to mu naught I plus epsilon naught mu naught d phi e dt. Now what this says is that there are two ways to make a magnetic field. One way, this term here, is to have a moving electric charge. The other way is to have a time-varying electric flux. Either of these ways will create a magnetic field. In both cases, because of this path integral nature here, the magnetic field line that you get will be one that loops back on itself. So it doesn't start or end anywhere, it just loops on itself. Consistent with what Gauss's law for magnetic fields is saying, which is that since there are no magnetic charges, there are no places that magnetic field lines can start or stop. Now this is cool enough as it is. We can see here that there is an interrelationship between electric and magnetic fields. If I were to say to have a time-varying magnetic field, this would create a time-varying flux, which would induce an electric field. And similarly, if I have a time-varying electric field, that creates a time-varying flux that induces a magnetic field. So it turns out that the electric and magnetic fields, although a lot of the times you can treat the electric and magnetic forces as separate things, they aren't completely separate. In fact, they are intertwined in this way. Now, where we're going to be going with this in the next series of videos is to focus very carefully on Faraday's law and the Ampere Maxwell law. Let's say, for instance, you have a magnetic field that varies sinusoidally with time. You take the derivative, that's going to be a cosine. All right, we'll ignore the minus signs for the moment here. They come out in the wash. But let's say you have a magnetic field that varies as sine of t. Take the derivative, you get yourself a cosine. Well, that means that my electric field that I'm inducing is varying as a cosine. But wait, the Ampere Maxwell law says that a time-varying electric field, so this is going as a cosine here, take the derivative, I'm going to end up with a sine. Again, I'm playing fast and loose with the plus and minus signs, but we'll sort them out later. It's going to give me a magnetic field that goes as a sine. So that means I get a time-varying magnetic field, which creates a time-varying electric field, which creates a time-varying magnetic field, which creates a time-varying electric field, which creates a time-varying magnetic field, and so forth and so on. And these fields will be at right angles to each other. This is starting to sound an awful lot like a wave kind of a thing, and you would be right. In the next series of videos, we will work to showing that this is indeed a wave-like entity. I'm being very careful here. While it is a wave, it turns out not to be a mechanical wave. It is just electric and magnetic fields varying in a way that is mathematically identical to a wave. But physicists still call it a wave. And it turns out that this wave will propagate at 1 over the square root of epsilon naught mu naught when we go and grind it all through. If you want to have a bit of a spoiler, go ahead, crunch those numbers into your calculator. So remember, it's 1 over root epsilon naught mu naught. See what the number you get is. So you can see here, it's the speed of light. So that led very much to the hypothesis that light waves are indeed transverse electromagnetic waves. In the previous series of videos, I referenced an experiment by Hertz that he created a whole tour de force of experiments that eventually led everyone to agree that, yes, this prediction is correct. Now, again, as a preview of coming attractions, this is going to lead to Einstein's special theory of relativity. These are just plain laws of physics. And this electromagnetic wave that's buried in the interrelationship between Faraday's law and the Ampere Maxwell Law, well, if everyone has the same laws of physics, this means everybody has to measure the same speed of light. This would mean even, say, if I were in a spaceship traveling at 99.9% of the speed of light, and I turn on my searchlight, if I measure the speed of the light leaving my spaceship, I get 3 times 10 to the 8 meters per second. And if you measure the speed of light from the searchlight leaving my spaceship, even though my spaceship's traveling at 99.9% of the speed of light, you will also measure that light is going at 3 times 10 to the 8 meters per second. Now, if it makes you feel any better, we will disagree about the color of the light coming out of the searchlight. I don't know if that made you feel any better or not, but it at least makes me feel a little better. But it is absolutely true. This fact that everybody has to have the same speed of light, combined with the Pythagorean theorem, will eventually lead us over to E equals mc squared, the one physics equation that you knew before you ever learned any physics. But I'm getting ahead of myself there, and that is a preview of coming attractions. Now, I would like to pivot for the rest of this video and look at the Lorentz Force Law. A lot of books out there, not all of them to their credit, but a lot of books out there really don't give Lorentz enough credit with the force law. So I want to motivate it so that we get a better sense of what it's saying. So this end, we're going to be thinking about 2 different observers. One of them will be moving at a constant velocity with respect to the other one. And following classic physics tradition, the names of the observers are S and S prime. S is the one that the narrator says is stationary, and S prime is the one that the narrator says is moving. So let's just go ahead and imagine that we have a magnetic field pointing into the screen like that. And let me just create a quick dividing line here between how S is going to see this and how S prime is going to see this. All right, so let's say we have a positive charge. So we got a charge plus Q, and it is moving to the right with velocity V in our uniform magnetic field. Well, it's a good time as any for some more right-hand rule practice, I suppose. So why don't you go ahead and tell me which way the magnetic force points? Okay. So I hope we are in agreement that the magnetic force acting on the charge points up. So that's QV cross B. So this is our observer S, who is stationary with respect to the magnetic field. S sees, so I'm going to draw S's coordinate system here. S sees the charge as moving to the right at velocity v. Now I want to think about our companion observer, S prime. S prime, and I'm drawing S prime's coordinate system here. I'm going to have S prime moving to the right at that same velocity v. So thinking back to velocity addition from mechanics, what would S prime say the velocity of that charge is? Yeah, that S prime would say the velocity of that charge is 0. So now let's go over here to how S prime will be looking at this. I'm not going to draw in a magnetic field here at the moment because, well, it'll become clear in a second. So let's say that we've got our charge plus Q here. Is S prime going to say that there is a force? Well, first off, let's just say, since we agree that in S prime's universe, the velocity of the charge is 0, how big of a magnetic force will S prime say the charge feels? Yeah, 0. Well, that's weird. Because again, physics has to be consistent. In order to not break physics, I mean, we can't have this person saying, yeah, the charge is totally feeling a force up, and this observer, who is just merely moving to the right with respect to the charge, so it seems stationary to them, they would still notice a force up. It's like the same deal, like, say, you know, if you're riding a, if you see some daredevil moving along on a skateboard, tossing a ball up and down. Pro tip, do not do this unless your name is Tony Hawk. The broken bones you save will be your own. But imagine Tony Hawk tossing a ball straight up and down while riding a skateboard in a nice straight line. Tony would say that he's tossing the ball straight up and down, but you, seeing Tony go by you and the ball going by you, would say the ball is going in a parabola. However, what you both absolutely agree on is that the ball is feeling a force straight down. In this case, the force of gravity. And your disagreement about trajectory is merely because of the difference in perspectives. So we've got the same issue here. You both agreed, you and Tony Hawk both agreed the ball felt a force of gravity. Here, we definitely have to agree that the charge felt a force. And it's got to be the same force, so I'm going to just draw that. But now, if you're S prime and you're saying that the charge isn't moving, at least initially, what are you going to blame the force on? Pause the video and come back with your idea. Yeah, so what S prime is going to have to do is they're going to blame this on the electric force. They're going to say, hey, I saw an electric charge that was initially stationary moving up. I know it can't be the magnetic force, so it's got to be the electric force. So S prime would notice that there was an electric field pointing up. How strong would this electric field have to be? Well, we can compare the terms. This electric field pointing up would point the same way as this force. Okay, that's good. So we would need the electric field that S prime sees to be equal to V cross B, like so. And this is if there wasn't an electric field already. Now, if there was an electric field already, we would then be saying that S prime would see an electric field that is equal to E plus V cross B. This gives rise to our Lorentz Force Law. So the combined electromagnetic the electromagnetic force, and I'm going to put it that way, acting on a charged particle is equal to Q times E plus V cross B. But what's going on here is that in some very real sense, the reason that, at least to S prime here, that this is because electric and magnetic fields transform into each other. This is what the electric field is that you would see if you were in the frame of the charge. So no charge. Every charge is going to say it's stationary, right? So every charge is going to say it only ever feels electric fields acting on it. However, this is the strength of the electric field that it sees. This is why the Lorentz Force Law is much more profound than some books will say. Some books will just say, oh, you add up the electric and the magnetic forces and you get the Lorentz Force Law. Yes, but it's much more profound. It's saying that in the frame of the charge, the only force there is electric, but that electric charge is seeing a different electric field than than you would be seeing in a frame where you see the charge as moving. So this is a big deal. At the end of the day, it turns out that relative to the charge, it's always the electric force. It's just that what we say the electric field strength is and what the charge says the electric field strength is are different. And this is actually our first hint of what's going on with relativity. What we're catching on to here is that different observers are literally having different experiences of space. Our observer S here said, hey, this is a magnetic field. Our observer S prime said, oh, no, it's totally an electric field. Who's right? They both are. But just like we've had before with these kinds of transformations, it'll be possible for both observers to compare notes and predict what the other observer sees. Now, there is a corresponding inverse transformation that is much harder to come to argue for, so I'm not going to do that here. I may, as we go through relativity, come back and do a little bit more to try to motivate the Lorentz Force Law after we've seen some relativity. It turns out that a way that you can argue for this is that the magnetic field is actually a relativistic effect that shows up even when you've got the excruciatingly slow speeds of the electrons in a typical wire that are moving at fractions of a millimeter a second. You'd think that wouldn't matter. It basically doesn't matter in anything else ever. But it turns out to matter here. So we'll see if we covered that. But I at the very least wanted to show you that there is more going on under the hood. The electric and magnetic fields transform into each other depending on how different observers are experiencing space. And so this is our very first hint that different observers actually have different experiences of space. Alrighty, so in the next series of videos, we are going to take the Maxwell equations and come up with light being an electromagnetic wave. See you over there.